Tonight, we're going to look into the darkest place in the universe. Not a metaphor, not a poetic image, a real place. A point in space where gravity has grown so extreme that not even light, the fastest thing that exists, can turn around and escape. A place where the laws of physics, every equation we have ever written, every model we have ever trusted, quietly stop working. And for the first time in human history, we aimed the most powerful telescope ever built directly at that darkness. And what we saw, what came back, shocked the scientists who spent their entire careers preparing for that moment. By the end of tonight, you're going to understand exactly why what the James Webb Space Telescope found near black holes has forced researchers around the world to sit back, go quiet, and reconsider things they thought were settled. You're going to understand why there are galaxies that should not exist. Why light is doing something at the edge of a black hole that our best model said was impossible, and why the black hole sitting at the centre of our own galaxy, 26,000 light-years from the bed you're lying in right now, has been silently shaping everything around you for longer than the Earth has existed. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now let's begin. There is a moment in every great act of human curiosity when someone has to make a decision. Not a small decision, not the kind you make quickly and forget by morning. A decision that carries the weight of decades of work, billions of dollars of engineering, and the quiet, terrifying possibility that the answer you find will be nothing like what you expected. That moment came for the James Webb Space Telescope on a night that looked, from the outside, like any other night in the control rooms of NASA and the Space Telescope Science Institute. Technicians at their screens, coffee going cold, numbers scrolling across monitors that very few people in the world were trained to read. And then, slowly, the telescope turned. It had taken 30 years to build the machine that was turning. 30 years of arguments and budget cuts and redesigns and one devastating delay after another. There were moments when the whole project nearly collapsed under its own ambition. Engineers who had given the best decades of their careers to a single golden mirror array, a folded structure of 18 hexagonal segments coated in a layer of gold so thin it exists at the boundary between matter and almost nothing. A sunshield the size of a tennis court, designed to keep the telescope colder than anything in the solar system, colder than Pluto, colder than the dark side of the moon, and all of it, every component, every compromise, every solved problem and every sleepless night, had been launched on a rocket on the 25th of December, 2021, folded into a shape small enough to fit inside a fairing, and sent 1 million miles from Earth to a point in space called L2, where it would spend years staring into distances that make the mind go quiet. But on the night we're talking about, Webb was not staring at a distant galaxy cluster for its own sake. It was not searching for the chemical signatures of water on a planet orbiting another star, though it has done that too. On this night, the telescope was being pointed towards something that astronomers had spent their entire professional lives theorizing about, modeling, arguing over, and never quite fully seeing. It was being pointed toward a black hole, and not just any black hole. One of the most extreme environments in the known universe, a place where space itself curves so sharply that it closes back on itself like a wound that cannot heal. A place where, if you crossed a certain invisible line, the concept of direction would lose all meaning. There would be no up, no out, no way back, only inward, forever, toward a centre that our mathematics can describe but cannot truly explain. Here is the thing most people do not realise about black holes. We have known they exist in the mathematical sense for over a century. Albert Einstein's general theory of relativity, published in 1915, contained within its equations the theoretical possibility of an object so dense that nothing could escape it. Einstein himself was uncomfortable with the implication. He did not fully believe the universe would allow something so extreme to actually form, but the universe, as it turns out, does not consult physicists before deciding what to do. Black holes are real. They form when massive stars die in catastrophic explosions, and their cores collapse inward under gravity so intense that the atomic structure of matter itself fails. Protons and neutrons and electrons are crushed together past any boundary we understand, down to a point of infinite density called a singularity, and surrounding that singularity at a specific distance determined by the mass of the object sits the event horizon, the point of no return. Cross it, and you are gone from our universe in any meaningful sense. For most of the history of astronomy, black holes were invisible. By definition, they emit no light. You cannot photograph them the way you photograph a star or a nebula. You can only infer them, trace their influence, watch the way they warp the light of objects behind them, or pull surrounding gas into glowing spirals of superheated material called accretion disks. For decades, that indirect evidence was all we had. And then, in April of 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole's shadow, a dark circle surrounded by a glowing orange ring of bent light, at the centre of a galaxy called M87, 55 million light-years away. The world stopped for a moment when that image was published. Scientists wept in press conferences, because for the first time, human beings had actually seen the shape of an event horizon, the boundary between our universe and the unknown. But that image, extraordinary as it was, had its limits. The Event Horizon Telescope is a radio telescope array. It sees in radio waves. It cannot see in infrared light, which is where most of the thermal and chemical story of the universe around a black hole gets told. It cannot peer into the structures of the accretion disk with the kind of sensitivity needed to test the deepest predictions of physics. It cannot look far enough back in time to see how black holes behaved when the universe was young. James Webb can do all of those things, and that is precisely why, on the night we're discussing, scientists around the world held their breath and waited for the data to come in. Because Webb was not just going to see a black hole, it was going to see into it, or as close to into it as the laws of physics will permit anything built by human hands to see. What came back changed things. That is not an overstatement, and it is not marketing language. The data Webb returned from its observations of black hole environments, including the supermassive black hole at the centre of our own Milky Way galaxy and black holes in the early universe billions of light-years away, revealed things that the models had not predicted. Things that made astronomers go back to their equations and ask uncomfortable questions. There were galaxies that existed too early. There was light behaving in ways that pushed against the edges of what general relativity said was possible. There was evidence that the relationship between black holes and the galaxies around them was stranger, more intimate and more fundamental than anyone had fully understood. And there was, at the centre of all of it, the same quiet, terrifying truth that has followed every great astronomical discovery in human history. The universe is stranger than we imagined, and we have only just begun to look. So tonight, we're going to take that journey together. We're going to start from the beginning, from what a black hole actually is, and how we came to know it exists, and we're going to follow the story all the way to the data that arrived from a telescope sitting 1 million miles away in the cold dark between the Earth and the Sun. We are going to go slowly. There is no rush here. The cosmos has been waiting 13.8 billion years for someone to look at it this carefully. It can wait a few more hours while we find our footing. And by the time this night is over, I think you will understand not just what Webb saw, but why it matters. Why it changes the story we tell about where we came from, what surrounds us, and what might be waiting at the edges of everything we think we know. Let's slow down for a moment. Before we go any further into what Webb found, before we talk about the shocking data and the galaxies that shouldn't exist, and the light doing things it isn't supposed to do, I want to make sure we are standing on solid ground together. Because black holes are one of those subjects where the words get used so often, in so many science headlines and documentary narrations and late-night conversations, that people sometimes feel like they understand them when really what they have is a collection of dramatic phrases. Bottomless pit, inescapable, tears in space-time. These are evocative. Some of them are even accurate, but they don't quite tell you what is actually happening. And tonight, I want you to really feel what a black hole is. Not just know the word. Feel the concept in your body the way you feel the difference between a cool room and a cold one. Start here. Gravity is not a force in the way most of us were taught to think about it. When you were young, you probably learned that gravity is a pulling force, something that massive objects exert on each other across space, like invisible hands reaching out and drawing things together. That picture is useful. It gets you through a lot of everyday physics, but it isn't quite right. Einstein showed us something more accurate and more strange. Gravity, he said, is not a force at all. It is a curvature. Mass bends space-time the way a heavy object bends a stretched rubber sheet. The Earth doesn't pull the Moon toward it. The Earth curves the space around it, and the Moon follows the curve. Everything that moves through space follows the local shape of space-time, and where mass is concentrated, that shape curves more sharply. This is the foundation. Hold on to it, because it is the key to understanding everything that happens at a black hole. Now imagine you have a star, not our Sun, which is a modest, medium-sized star by cosmic standards, but something much larger. A star 20 or 30 times the mass of the Sun, burning at temperatures of millions of degrees at its core, fusing hydrogen into helium and then helium into heavier elements in a chain of nuclear reactions that produces enough energy to hold the entire star up against its own gravity. For millions of years, this balance holds. The outward pressure of all that nuclear fire pushing against the inward pull of all that gravity. It is a kind of standoff, a truce written in plasma and light. But eventually the fuel runs out. The core has nothing left to burn, and in a fraction of a second, not a long fraction, we're talking about less than a second, the core collapses, all that mass falls inward, and the outer layers of the star, no longer supported from below, come crashing down after it, and then rebound in an explosion so violent it can briefly outshine an entire galaxy. We call this a supernova, and what is left at the centre, if the original star was massive enough, is a black hole. Here is where it gets strange. The core that remains after the collapse has no internal pressure left to push back against gravity. None. Every force that could resist the inward pull has been overwhelmed, and so the collapse continues. The material at the centre compresses further and further, past the density of an atomic nucleus, past any state of matter we have a name for, down to a mathematical point of infinite density called a singularity. Infinite density means infinite curvature of space-time at that point. Our equations reach that word, infinite, and essentially give up. They produce results that cannot be physically interpreted. The singularity is where general relativity, our best description of gravity, breaks down completely. It is a place where the universe is doing something real, something physical, but we do not have the mathematics to describe what that something is. And that honest admission that we don't know is one of the most important things in all of science. Surrounding the singularity, at a distance determined by the object's mass, is the event horizon. This is not a physical surface. You could not touch it or land on it. It is a boundary defined entirely by mathematics, by the point in space where the escape velocity, the speed you would need to travel in order to break free of the gravitational pull, equals the speed of light. Inside that boundary, escape velocity exceeds the speed of light. And since nothing in the universe travels faster than light, nothing inside the event horizon can ever get out. Not matter, not radiation, not information, not even a description of what is happening in there. The event horizon is the universe's most absolute one-way door. Cross it in the wrong direction, and the concept of return becomes meaningless. Now here is something I want you to sit with for a moment, because most people don't think about it this way. The event horizon of a black hole is not a wall. It is not a crushing surface. If you were falling toward a stellar mass black hole, one formed from a single dying star, you would be torn apart by tidal forces long before you reached the horizon. But if you were falling toward a supermassive black hole, one with the mass of millions or billions of suns, the event horizon is so large that the tidal forces at the boundary are actually relatively gentle. You could cross the event horizon of a supermassive black hole and feel nothing unusual in that instant. No dramatic moment, no flash of light, no physical sensation of crossing a threshold. The terrifying part is what comes after. Once inside, every path through space-time, every possible direction you could move, curves toward the singularity. Forward in time becomes inward toward the centre. You cannot turn around any more than you can travel backward in time. The singularity is not a place in space you are approaching. It is a moment in your future that you cannot avoid. The mass of black holes varies enormously. Stellar black holes formed from individual dying stars typically range from a few times the mass of our Sun up to perhaps 100 solar masses. Then there are intermediate black holes, still poorly understood, with masses in the thousands to hundreds of thousands of solar masses. And then there are the supermassive black holes, the true giants, sitting at the centres of nearly every large galaxy we have ever examined, including our own. These objects range from hundreds of thousands to tens of billions of times the mass of the Sun. The one at the centre of our Milky Way, Sagittarius A star, has a mass of roughly 4 million suns. The one at the centre of the galaxy M87, the one we imaged in 2019, has a mass of approximately 6.5 billion suns. Its event horizon is so large that our entire solar system, everything from the Sun to the outermost edge of the Oort cloud, would fit inside it with room to spare. This is what we are dealing with. Not metaphors, not exaggerations for dramatic effect. Real objects, obeying real physics, sitting at real coordinates in the sky above you right now, invisible but undeniably there, anchoring galaxies, bending light, warping time, and waiting, as they have waited for billions of years, for something with enough curiosity and enough engineering to finally look at them closely. James Webb is that something, and what it found when it looked is what we're here to talk about tonight. To understand what Webb changed, you have to understand what came before it. Not because the telescopes that preceded Webb were failures, they were extraordinary achievements, each one pushing the boundaries of what humanity could see and know, but because every instrument has a limit, and those limits are not flaws, they are invitations. Every time we hit the edge of what a telescope could show us, we built a better one. And every time we built a better one, the universe revealed another layer of itself that we had not known was there. This is the rhythm of astronomy. Reach, find the edge, build further, reach again. Webb is the latest extension of that rhythm, but it did not arrive in a vacuum. It arrived at the end of a very long chain of looking. The story of modern black hole observation begins, in many ways, with a telescope that was itself born in controversy. The Hubble Space Telescope launched in April of 1990 aboard the Space Shuttle Discovery. It was supposed to be a revolution, a telescope above the blurring distortion of Earth's atmosphere, able to see the universe with a clarity no ground-based instrument could match. And then, within weeks of its launch, scientists discovered that the primary mirror had been ground to the wrong shape. Not by much. The error was smaller than 1/50th the width of a human hair, but in optics, that is catastrophic. The images Hubble returned were blurry. The press called it a national embarrassment. Congress called it a scandal. And for 3 years, the most expensive telescope ever built drifted in orbit, producing science that was good but nowhere near what had been promised. The repair mission came in December of 1993. Astronauts from the Space Shuttle Endeavour conducted 5 spacewalks over 11 days, installing corrective optics that worked like contact lenses for the flawed mirror. When the first corrected images came back, the reaction at NASA was described by people who were in the room as something close to disbelief. Stars that had been fuzzy blobs became sharp points of light. Galaxies resolved into spirals with individual structure. The universe snapped into focus, and Hubble immediately began contributing to black hole science in ways that transformed the field. It provided evidence that supermassive black holes are not rare exceptions, but standard features of large galaxies, likely present at the centre of nearly every one. The relationship between a galaxy and its central black hole turned out to be intimate in ways no one had fully anticipated. But Hubble sees primarily invisible light and ultraviolet. It is not designed to look at the extremely hot, extremely energetic environments that surround actively feeding black holes, environments that pour out X-rays and gamma rays rather than visible light. For that, astronomers needed a different kind of eye. Enter the Chandra X-ray Observatory, launched in July of 1999. X-ray astronomy is a strange discipline because X-rays from space cannot penetrate Earth's atmosphere, which is fortunate for life on Earth's surface but inconvenient for astronomers. To detect them, you need to be above the atmosphere. Chandra was placed in an elliptical orbit that takes it nearly a third of the way to the Moon, and it was equipped with mirrors designed not to reflect X-rays directly, but to catch them at a grazing angle, the way light skips off the surface of still water at a low angle. The engineering is breathtaking in its ingenuity. Chandra transformed our understanding of black hole activity. It revealed the superheated gas swirling around black holes in exquisite detail, showing jets of plasma being fired from the poles of supermassive black holes at close to the speed of light, jets that extend for hundreds of thousands of light years and pump enormous amounts of energy into the surrounding galaxy. It observed black holes actively consuming matter, the process astronomers call accretion, and measured the temperatures of that in falling material. Millions of degrees, in some cases, hundreds of millions. Chandra showed us black holes not as silent voids, but as some of the most energetically violent environments in the universe, places where matter is compressed and heated to extremes that dwarf anything achievable in a laboratory. And yet, even Chandra could not show us the shape of a black hole itself. It could map the environment, it could not photograph the thing at the centre. That achievement belonged to a completely different kind of instrument. In April of 2019, the Event Horizon Telescope collaboration released an image that stopped the world. A dark circle surrounded by an asymmetric ring of glowing orange light set against the black background of space. It was the shadow of the supermassive black hole at the centre of the galaxy M87, 55 million light-years away, an object with a mass of 6.5 billion suns. The Event Horizon Telescope is not a single instrument. It is a global network of radio telescope arrays spread across 4 continents, from Hawaii to Chile to the South Pole, synchronized so precisely that together they function as a single dish the size of the entire Earth. The resolution required to capture that image was equivalent to reading a newspaper in New York from a cafe in Paris. Scientists and journalists and ordinary people around the world looked at that orange ring and felt something shift. We had seen the shape of the unseeable, the boundary between our universe and whatever lies beyond. But the Event Horizon Telescope image, extraordinary as it was, raised as many questions as it answered. It was a radio image. It showed the broad strokes of the light ring around the shadow, but it could not reveal the detailed structure of the material spiraling into the black hole, the chemical composition of the accretion disk, or the behavior of light at energies beyond the radio band. It could not look back in time to see how black holes in the early universe compared to the ones we see today. And it could not look at our own galaxy's central black hole, Sagittarius A star, with the kind of resolution that would test the deepest predictions of Einstein's equations. These were the open doors. These were the questions sitting on the table when James Webb finally reached its operating position and opened its golden eye. Every telescope that came before had handed it a list of things to check, and Webb, patient and precise and cold beyond anything we had sent into space before, began to work through that list one observation at a time. There is a particular kind of human stubbornness that does not look like stubbornness from the outside. It looks like patience. It looks like decades of quiet, grinding work on a problem so complex that most people who encounter it in passing assume it must be nearly finished, because surely no serious endeavour could take this long. The James Webb Space Telescope was first proposed in the mid-1990s, when Hubble was still relatively new and the scientific community was already asking what would come next. The original plan called for a launch around 2007. The telescope that finally left Earth did so on the 25th of December, 2021. 14 years late, billions of dollars over budget, and more technically ambitious than anything humanity had ever attempted to place in orbit. The delay was not negligence. It was the unavoidable consequence of trying to build something that had never existed before. The central challenge Webb was designed to solve is the problem of infrared astronomy. Light, as you probably know, comes in many forms beyond the narrow band of wavelengths your eyes can detect. Visible light, the reds and oranges and yellows and greens and blues you see, occupies a tiny slice of the full electromagnetic spectrum. Beyond the red end of visible light lies infrared radiation, which we experience as heat rather than colour. Objects that are too cool or too distant or too old to shine brightly in visible light still emit infrared radiation. And here is the critical fact for understanding why Webb matters. The universe is expanding. As light travels across billions of light-years of expanding space, its wavelength stretches. Visible light emitted by a galaxy 13 billion years ago arrives at our detectors today not as visible light but as infrared. To see the earliest galaxies, to look back at the universe when it was young, you must be able to see in infrared. Hubble cannot do this well. Webb was built to do nothing else. But infrared astronomy from space comes with a brutal engineering constraint. Infrared detectors are exquisitely sensitive to heat. Any warmth, any at all, from the telescope's own structure or electronics or mirrors, drowns out the faint infrared signals arriving from billions of light-years away. It is like trying to listen to a whisper from across a continent while standing next to a jet engine. To eliminate the noise, the telescope itself must be made extraordinarily cold. Webb's operating temperature for its primary instruments is roughly minus 233 degrees Celsius. That is 40 Kelvin above absolute zero. To put that in terms that means something, the surface of Pluto, the coldest large body in our solar system, sits at around minus 223 degrees Celsius. Webb's detectors run colder than Pluto, colder than anything that occurs naturally in our solar system. Achieving and maintaining that temperature in the engineering environment of space required a solution that is still almost impossible to fully appreciate from the outside. The solution is the sun shield, a 5-layer membrane structure roughly the size of a tennis court, made from a material called Captain coated in aluminum and silicon, designed to block the light and heat of the sun, the Earth and the Moon simultaneously and keep the telescope in permanent stable shadow. Each layer of the sun shield reduces the temperature by a factor of roughly 10, so that by the time you reach the 5th layer and the telescope structure beyond it, the temperature has dropped from 230 degrees Celsius on the sun-facing side to the minus 230 degrees required by the instruments. The sun shield had to be folded into a shape small enough to fit inside a rocket fairing, roughly 5 meters across, and then unfold itself perfectly in space, with no human hands available to help. This unfolding process involved 344 single-point failures, mechanisms that had to work correctly the first time, in the cold vacuum of space, with no possibility of repair. Every single one of them worked. The primary mirror is perhaps the most recognizable element of Webb's design. 18 hexagonal mirror segments, each one 1.32 meters across, coated in a layer of gold approximately 100 nanometers thick. Gold was chosen not for its visual beauty but for its exceptional reflectivity in the infrared wavelengths Webb is designed to detect. Together, the 18 segments form a collecting surface 6.5 meters in diameter, a mirror nearly 3 times the width of Hubble's primary mirror and with roughly 6.3 times the collecting area. More collecting area means more photons, means fainter objects visible, means deeper into space and further back in time. Each of the 18 segments is individually adjustable to within nanometer precision by tiny actuators on the back, allowing the mirror to be tuned in space to a level of optical perfection that cannot be achieved during manufacturing on the ground. The alignment process, which took months after launch, required moving each segment by amounts smaller than 1/10 the diameter of a human hair. Webb was sent not to low Earth orbit, where Hubble lives, but to a gravitational point called L2, the second Lagrange point, located 1.5 million kilometers from Earth in the direction directly away from the Sun. At L2, the gravitational pulls of the Earth and the Sun combine in a way that allows an object to orbit the Sun in sync with the Earth, maintaining a constant position relative to both. This is important because it means Webb can always keep its sun shield oriented between itself and all 3 heat sources, Sun, Earth, and Moon, simultaneously. It also means Webb is far beyond the reach of any servicing mission. When something goes wrong with Hubble, astronauts can theoretically reach it. Webb is beyond any crewed spacecraft currently in existence. It launched fully knowing it could never be repaired. Every component had to work, and they do. When the first full-color science images from Webb were released on the 12th of July, 2022, the reactions from scientists were not the polished, composed responses of people managing their emotions for a press conference. They were the reactions of people who had spent their careers working towards something and were now, for the first time, seeing what they had actually built. Researchers described seeing details in distant galaxies that they had never expected to resolve in their lifetimes, structures in nebulae that rewrote their understanding of star formation, atmospheric data from exoplanets that opened new conversations about habitability. And then, quietly, systematically, Webb turned toward the black holes, toward the environments that push physics to its absolute limit, toward the questions that the telescopes that came before had identified but could not fully answer. The eye was open, the data was flowing, and the universe, patient as always, began to show us things we were not entirely prepared to see. Somewhere above you right now, hidden behind the dense band of stars and gas and dust that forms the inner plane of our galaxy, there is something that has been there longer than our solar system has existed. You cannot see it with your eyes. You cannot see it with an ordinary telescope. It emits no visible light of its own, gives no obvious signal, announces its presence in no way that is available to unaided human senses, and yet every star in the Milky Way, all estimated 400 billion of them, moves in relationship to it. Our own Sun, along with everything gravitationally bound to it, orbits it once every 230 million years, tracing a vast loop through the galaxy at a speed of roughly 828,000 kilometers per hour. We've been going around it since before the first dinosaurs appeared on Earth. We will still be going around it long after the Sun expands and swallows this planet. Its name is Sagittarius A star, and it is a supermassive black hole with a mass of approximately 4 million times the mass of our Sun. 4 million solar masses. Let that number breathe for a moment. Our Sun is already almost incomprehensibly large. Its diameter is about 109 times the diameter of Earth. You could fit 1,300,000 Earths inside it. The Sun contains 99.8% of all the mass in the entire solar system. Everything else, all 8 planets, all the moons, all the asteroids, all the comets, all the dust, is the remaining 0.2%. And Sagittarius A star has the mass of 4 million of those suns, compressed into a region of space roughly the size of our solar system's inner zone. Its event horizon, the boundary of no return, has a radius of approximately 12 million kilometers. That sounds enormous. Compared to the scale of the galaxy, it is almost nothing. A needle lost in a field the size of a continent, but in absolute terms 12 million kilometers is nearly 8 times the distance from the Earth to the Moon. We cannot see Sagittarius A star directly in visible light because the galactic center is shrouded behind 26,000 light-years of interstellar dust and gas, material so dense that visible light from the center is absorbed almost completely before it reaches us. For most of human history, we had no idea what was at the center of our galaxy at all. The core was invisible. The question was not even properly formed yet because we did not know enough to ask it. Then, in the 1970s and 80s, radio telescopes began detecting a compact, extremely bright radio source at the galactic center, something small and intensely energetic sitting right at the middle of everything. Astronomers named it Sagittarius A star, using the asterisk to denote that it was a particularly bright and interesting radio source within the larger Sagittarius A complex of structures. For years, its true nature was debated. The evidence for a black hole was suggestive but not conclusive. The conclusive evidence came from decades of painstaking observation by 2 groups working independently. One led by Reinhard Genzel at the Max Planck Institute in Germany, and one led by Andrea Ghez at UCLA. Beginning in the 1990s and continuing for over 2 decades, both groups used infrared telescopes equipped with adaptive optics, systems that correct for atmospheric blurring in real time to track the motions of individual stars in the dense cluster around the galactic center. What they found was extraordinary. Stars near the center were moving at speeds of thousands of kilometers per second, following tight elliptical orbits around a point that emitted no light at all. One star, designated S2, was observed completing a full orbit in roughly 16 years, swooping to within about 120 astronomical units of the central object at its closest approach. The orbital dynamics were unambiguous. The mass required to produce those motions, concentrated in a volume no larger than our solar system, could only be explained by a supermassive black hole. Genzel and Ghez shared the Nobel Prize in Physics in 2020 for this discovery. And then, in May of 2022, the Event Horizon Telescope collaboration released something that made the evidence not just conclusive but visible. An image of Sagittarius A star itself, or rather, of its shadow. A dark central region surrounded by a glowing ring of superheated material, the same basic structure as the M87 image from 2019 but far more challenging to produce. Sagittarius A star is much closer than M87, which might seem like it would make the imaging easier, but the problem is that the material around SGR A star moves much faster relative to the observation timescale, changing on timescales of minutes rather than days, making it much harder to capture a stable, averaged image. The team described it as trying to photograph a dog chasing its tail very quickly. The image they produced required combining data from 8 radio observatories across the globe and averaging thousands of individual snapshots to produce something coherent. When it was published, astronomers around the world had the rare experience of seeing for the first time the face of the thing that has been at the center of their galaxy their entire lives. but the Event Horizon Telescope image, like the Chandra data and the stellar orbit studies before it, showed only what radio and near-infrared instruments could show. The deeper physical story of Sagittarius A star, the behavior of its accretion flow, the nature of its intermittent flares, the way it interacts with the surrounding stellar population over time, the question of whether its current relative quiescence is typical or anomalous on cosmic timescales, all of that remained frustratingly incomplete. S-Gray star is, by the standards of supermassive black holes, surprisingly quiet. It is not actively devouring large amounts of material the way some galactic center black holes are. It sits there in a kind of low-energy state, occasionally producing brief infrared and X-ray flares when small amounts of gas or dust drift too close, but otherwise giving little away. Understanding why it is so quiet, and what that tells us about the relationship between black holes and galaxy evolution, was one of the primary motivations for pointing Webb toward the galactic center. When Webb observes Sagittarius A star, it is looking through 26,000 light-years of space at an object that formed before our solar system existed, that has been anchoring our galaxy since the Milky Way itself was young, and that sits at coordinates we can now point to with precision. Right ascension, 17 hours, 45 minutes, 40.04 seconds, declination negative 29 degrees, 0 minutes, 28.1 seconds. On a clear night, that point in the sky lies in the constellation Sagittarius, low on the southern horizon, as seen from the northern hemisphere, toward the heart of the glowing band of the Milky Way. You are orbiting that point right now. You've been orbiting it your entire life. Every person who has ever lived on this planet was in gravitational relationship with it from the moment they were born. It is the still center around which 400 billion stars quietly turn, and tonight we are going to look at what Webb found when it finally stared back at it. Science is often described as a process of asking questions and finding answers, but that description leaves out something important. Before the question, before the methodology, before the data collection, and the peer review and the published paper, there is a moment that rarely gets discussed in textbooks or press releases. There is the moment when a scientist decides what to look at, and in astronomy, where telescope time is a finite and ferociously contested resource, that decision carries enormous weight. Every hour Webb spends observing one target is an hour it cannot spend on another. The telescope's schedule is planned years in advance, negotiated through competitive proposal processes where researchers from around the world argue the scientific merits of their particular question against every other question being asked simultaneously. To get Webb time pointed at a black hole, you have to convince a committee that your black hole question is more important, more timely, or more tractable than everything else on the list. That is not a small thing to ask. The scientific case for pointing Webb at black hole environments rested on several converging lines of inquiry that had been building for years before the telescope ever launched. The first was the question of accretion physics. We know that material falling into a black hole forms an accretion disk, a flattened structure of superheated gas spiraling inward like water circling a drain, except the temperatures involved are not a few degrees above room temperature but millions of degrees above absolute zero. We know this material radiates energy across a wide range of wavelengths as it falls, but the detailed physics of how that energy is generated, how the magnetic fields in the disk behave, how material transitions from the outer disk to the inner edge, and finally across the event horizon, all of that remained poorly constrained by observations. Webb's infrared sensitivity offered a new window into the thermal and chemical structure of accretion flows that no previous instrument could match. The second line of inquiry was the flaring behavior of Sagittarius A star. Ground-based infrared observatories had already detected something puzzling about the galactic center black hole. It produces brief, bright flares, sudden increases in infrared and X-ray brightness that last anywhere from a few minutes to a few hours and then subside. These flares happen several times per day. Their origin is not fully understood. The leading hypothesis is that clumps of hot plasma, called hotspots, form in the innermost region of the accretion disk and orbit the black hole at close to the speed of light before eventually being consumed. If that is correct, the timing and brightness pattern of the flares contains encoded information about the geometry of space-time at the very edge of the event horizon. Webb, with its ability to monitor a Scar A star continuously across multiple infrared wavelengths simultaneously, was perfectly positioned to capture these flares with unprecedented detail and test whether the hotspot model was correct. The third and perhaps most consequential line of inquiry was the behaviour of black holes in the early universe. The James Webb Space Telescope was designed from the beginning to look back to the cosmic dawn, the era just a few 100 million years after the Big Bang when the first stars and galaxies were forming. Theorists had constructed detailed models of how this process should have unfolded, models that predicted what the first galaxies should look like: small, irregular, not yet fully formed, containing black holes that were still relatively modest in size. These models were not guesses. They were the product of decades of increasingly sophisticated computer simulations, informed by everything we knew about physics, gravity, gas dynamics, and cosmological structure formation. They were, as far as anyone could tell, well grounded in reality. The decision to test them with Webb was therefore not seen as risky. The models were expected to be confirmed, with perhaps minor adjustments at the margins. This turned out to be a significant miscalculation. There was also, beneath the formal scientific justifications, a quieter motivation that researchers are sometimes reluctant to state in grant proposals but will admit to in conversation. Black holes are the places where our best theories break down. General relativity, which describes gravity and the large-scale structure of space-time, predicts the existence of black holes but cannot describe what happens at the singularity. Quantum mechanics, which describes the behaviour of matter and energy at the smallest scales, works everywhere except in the extreme gravity near a black hole. These two pillars of modern physics, each individually the most precisely tested theory in the history of science, are fundamentally incompatible with each other in the environment of a black hole, and every time we observe a black hole more carefully, we are probing the seam where they fail to fit together. No scientist who has spent their career at that seam could look at Webb's capabilities and not feel something pull toward it. The desire to look is not just professional, it is something closer to compulsion. The planning for Webb's black hole observations involved not just choosing targets, but developing entirely new observational strategies. Sagittarius A* presented a particular challenge because it sits behind so much intervening dust that even infrared light is significantly absorbed before reaching the telescope. Observers had to select specific infrared wavelengths where the dust is relatively transparent, what astronomers call atmospheric and galactic windows, and design their observations to spend enough time on target to catch multiple flares, while also maintaining the precise pointing stability that Webb requires. The telescope does not hunt or track moving objects the way a camera follows action. It locks onto a fixed position in the sky and stares with absolute precision. Keeping it aimed at the galactic centre while the flares came and went required careful coordination between the observing team and the telescope's operations staff. For the early universe black hole targets, the strategy was different. Researchers identified fields of sky that had been previously observed by Hubble and other telescopes, regions where the galaxy density was high and the scientific context was already rich, and designed deep Webb exposures that would push into the infrared depths that no previous telescope had reached. The goal was to find the earliest black holes, the seeds, the original population that grew over billions of years into the supermassive monsters anchoring galaxies today. Finding them would confirm the models. Not finding them, or finding something unexpected, would mean the models were wrong in some fundamental way. Most researchers, if they were being honest with themselves in the quiet hours before the data arrived, expected confirmation. The models were good. The physics was solid. The universe surely would behave as predicted. It did not. And the moment the data began coming in, the quiet confidence in those control rooms began to shift into something more complicated. Not panic, not confusion exactly. Something more like the particular feeling you get when a familiar room is rearranged in the dark and you reach for a wall that is not quite where you expected it to be. Everything is still there, but the map is wrong. And you realise, with a mixture of unease and excitement that is unique to science and to very few other human activities, that you're going to have to draw it again from the beginning. The data does not arrive the way you might imagine. There is no dramatic moment in a control room where a single image suddenly appears on a screen and everyone gasps. The process is slower than that, more technical, more layered, and in many ways more strange. Raw data from Webb travels from the telescope to the ground station at White Sands, New Mexico, then to the Space Telescope Science Institute in Baltimore, Maryland, where it is processed, calibrated, and distributed to the science teams who requested the observations. What arrives first is not a picture, It is a stream of numbers, photon counts, detector readings, spectroscopic data broken into thousands of individual wavelength channels. The image, the thing you can actually look at, is something that gets constructed afterward, layer by layer, by software and by human judgment about how to translate the raw signal into something a human visual system can interpret. The first person to see a Webb observation of a black hole environment did not see a glowing ring. They saw a spreadsheet, and they had to know what they were looking at well enough to understand why those particular numbers were extraordinary. For the observations of Sagittarius A*, the first usable science data began arriving in 2022. During Webb's first year of operations, the telescope was directed at the galactic center multiple times as part of both dedicated observing programs and as a secondary target during other nearby observations. What the near-infrared camera, known as NIRCam, returned was a field of extraordinary density, millions of stars packed so closely together near the galactic center that they form an almost continuous glow of stellar light, a background so crowded that isolating individual objects requires sophisticated image processing algorithms. At the precise position of Sagittarius A*, the data showed something that ground-based observers had already detected in cruder form but had never seen with this clarity: infrared flares. Brief, bright, rapid variations in intensity at the exact coordinates of the black hole, each one a pulse of energy from the innermost edge of the accretion flow, each one carrying information about conditions within a few times the event horizon radius. The flares, when examined in detail, were striking. Some lasted only a few minutes, others persisted for an hour or more. Their brightness varied by factors of several times the baseline emission level, and the pattern of that variation was not random. There was structure in it. The rise and fall of each flare had a characteristic shape, and the timing between successive peaks showed a quasi-periodicity, a rough rhythm that repeated with some regularity but not perfectly, like a heartbeat that is recognizable as a heartbeat, even though no two beats are exactly identical. This quasi-periodicity had been hinted at in previous observations, but Webb's data showed it with a precision that allowed researchers to actually measure it. The period was consistent with what you would expect from a hotspot of plasma orbiting the black hole at the innermost stable circular orbit, the closest point at which matter can orbit without immediately spiraling inward. That orbit takes approximately 30 minutes to complete. The flare pattern matched. For the accretion disk observations more broadly, Webb's spectroscopic instruments provided something that imaging alone cannot: chemical fingerprints. The near-infrared spectrograph, NIR-SPEC, splits incoming light into its component wavelengths and measures the intensity at each one, producing a spectrum that reveals what elements and molecules are present in the material being observed, how hot that material is, how fast it is moving relative to the telescope, and whether it is moving toward or away from us. Applied to the environments around black holes, this spectroscopic data is enormously rich. It showed the superheated gas in the accretion flow containing ionized iron, hydrogen, helium, and other elements at temperatures of tens of thousands of degrees, moving at velocities that, in the innermost regions, represent significant fractions of the speed of light. The spectra showed Doppler shifts, the stretching and compressing of light wavelengths caused by the motion of the emitting material, that directly traced the orbital velocity structure of the disk. But it was not just the galactic center observations that produced striking first results. Webb was also directed at a class of objects called active galactic nuclei, galaxies in which the central supermassive black hole is actively and voraciously consuming material, pouring out so much energy that the nucleus outshines the entire surrounding galaxy by factors of hundreds or even thousands. These objects, also called quasars when seen at great distances, are among the most luminous persistent sources of energy in the universe. A single quasar can emit more energy per second than 1 trillion suns. They were common in the early universe and have become rarer as the universe has aged, and the available fuel around galactic center black holes has been consumed. Webb could see them at distances and redshifts, meaning look-back times in cosmic history that no previous infrared telescope could reach with this level of sensitivity. And the spectra Webb returned from these distant active nuclei showed the chemical and physical conditions of black hole accretion at epochs when the universe was less than 1 billion years old. The initial reaction among the science teams reviewing this data was a mixture of satisfaction and unease. The satisfaction came from the fact that Webb was performing exactly as designed. The data quality was extraordinary. The sensitivity exceeded pre-launch predictions in several wavelength ranges. The pointing stability, the ability of the telescope to remain locked on a precise position in the sky for hours at a time, was better than the specifications had required. Everything that could be verified against known sources and calibration targets confirmed that the instrument was working correctly. The unease came from something else. Some of the numbers coming out of the early universe observations were not matching the predictions. Galaxies were appearing in the data that seemed too bright, too massive, too structured for their apparent age. The first instinct of any careful scientist when confronted with unexpected results is to check for errors, bad calibration, contamination from nearby sources, misidentified redshifts. The teams went back through the data methodically, looking for the mistake, and in several key cases they could not find one. The data was clean, the galaxies were real, and they were not supposed to be there. That realization, quiet and precise, as all important scientific realizations are, was the beginning of something that would force cosmologists to have very uncomfortable conversations about models they had trusted for decades. Here is something that sounds impossible the first time you hear it. Light that falls into a black hole can, under certain conditions, appear to come out the other side. Not through the event horizon. Nothing crosses the event horizon outward, and that rule is absolute. But light that passes close to a black hole without quite crossing that boundary, light that skims the edge of the most extreme gravitational field in the universe, does something that no human intuition is equipped to anticipate. It bends, not slightly. Not the way light bends passing through a glass of water or near the surface of the sun. It bends so severely along such extreme curvature of space-time that it can wrap around the black hole entirely, completing arcs of more than 180 degrees, and emerge on the side facing away from where it originated. An observer positioned correctly can see light from a source that is, geometrically speaking, directly behind the black hole. And Webb, with its extraordinary infrared sensitivity and its position 1,000,000 miles from Earth's atmospheric blurring, captured this phenomenon with a clarity that left researchers staring at their screens in silence. The technical name for this effect is gravitational lensing, but what happens near a black hole is lensing taken to an extreme that overwhelms the word's ordinary meaning. Conventional gravitational lensing, the kind first confirmed during the solar eclipse of 1919, when Einstein's prediction was tested by observing starlight bending around the sun, produces subtle deflections of a fraction of a degree. Near a black hole's event horizon, the deflection is not a fraction of a degree. It is multiple complete revolutions. Photons can orbit a black hole at a specific radius called the photon sphere, approximately 1.5 times the event horizon radius, where the curvature of space-time is exactly sufficient to bend light into a circular orbit. These photons do not orbit stably. Any slight perturbation sends them either spiraling inward toward the event horizon or spiraling outward to escape. But in that brief moment of near-circular orbit, they trace a path that is, by any intuitive measure, completely impossible. Light going sideways, light going backward, light doing things that light simply does not do anywhere else in the universe. What Webb detected in several black hole observations was the infrared signature of light echoes, sometimes called light reverberations, produced by this extreme bending. When a flare of energy erupts in the accretion disk of a black hole, that flare sends light outward in all directions. Some of that light travels directly toward the observer and arrives first, but some of it initially travels in other directions, bends around the black hole along multiple different paths of varying length, and arrives at the observer slightly later, carrying the same spectral signature as the original flare but delayed and subtly distorted by the different paths it travelled. By measuring the time delays between these echo signals and comparing their spectral characteristics, researchers can reconstruct the geometry of the region they came from. It is, in effect, a way of mapping the space-time geometry near the event horizon using light itself as the probe. No spacecraft could survive to make these measurements in situ, but the light carries the information out, encoded in timing and wavelength, and Webb is sensitive enough to read it. The echoes Webb captured around several active galactic nuclei were not just confirmation of a predicted effect. They were sharper, more detailed, and more structurally complex than models had suggested they would be. The reverberation mapping data revealed that in some systems, multiple distinct echo signals were arriving from what appeared to be different reflection surfaces within the accretion disk, surfaces at different distances from the black hole, each one encoding slightly different information about the local conditions. The innermost reflection signals were coming from regions so close to the event horizon that the photons carrying them had experienced measurable gravitational redshift, a stretching of their wavelengths caused by climbing out of an intense gravitational field before reaching Webb's detectors. This was not a theoretical prediction being confirmed from a safe distance. This was a direct measurement of space-time curvature within a few event horizon radii of a supermassive black hole, extracted from data gathered by a golden mirror floating in the cold dark 1,000,000 miles from Earth. There was another discovery embedded in Webb's black hole observations that produced a specific kind of quiet shock among relativists, physicists who specialize in the behavior of matter and light in extreme gravitational fields. General relativity predicts that a rotating black hole, which is to say essentially every black hole in the universe, since all the stars that form them are rotating and angular momentum is conserved in the collapse, drags the space-time around it into rotation as well. This effect is called frame dragging, or the lens-thirring effect, and it means that the region of space near a spinning black hole is not just curved but twisted, rotating along with the black hole like the water near a spinning whirlpool. The innermost region of the accretion disk, the material closest to the event horizon, should therefore show spectral signatures consistent with being in a region of significantly dragged spacetime. Webb's spectroscopic data from the nearest and best characterized active galactic nuclei showed precisely these signatures, at a level of detail that allowed researchers to make estimates of the spin rates of the central black holes. Some of them were spinning at close to the maximum rate permitted by general relativity. Their event horizons were, in the most precise physical sense, rotating at nearly the speed of light. The broader implication of all this, and the reason it produced not just scientific interest but something closer to vertigo among the researchers involved, is what it says about the nature of the region immediately outside the event horizon. For decades, the event horizon was treated somewhat abstractly, as a mathematical boundary rather than a physical surface. The popular conception of a black hole as a simple dark void, a passive absence of light, is technically accurate but deeply misleading. The region just outside the event horizon is one of the most physically active and energetically extreme environments in the universe. Magnetic fields of extraordinary strength thread through the accretion disk and connect to the black hole's rotation, extracting energy from the spin and launching it outward in the form of relativistic jets. Photons orbit, bend, echo, and escape with their wavelengths altered by gravitational fields stronger than anything else in existence. Matter is accelerated to significant fractions of the speed of light, compressed, heated, ionized, and ultimately consumed. And all of this is happening continuously, right now, in thousands of galaxies visible in any deep Webb image. When you look at a Webb deep field, one of those images showing thousands of galaxies arrayed across a patch of sky smaller than a grain of sand held at arm's length, many of those tiny smears of light contain at their centers a supermassive black hole, doing all of these things simultaneously, bending light around itself, flinging echoes outward, dragging space-time in rotation, and occasionally erupting in flares that briefly outshine everything around them. The universe is not a quiet place. It only looks quiet from where we are standing, behind all that distance. Up close, at the edge of a black hole, it is more violent and more strange than any human language was built to describe, and Webb is giving us for the first time the tools to read what the light escaping from that violence is trying to tell us. I want you to think about time for a moment. Not time in the abstract philosophical sense, but time as a physical thing, a dimension of the universe that behaves according to rules just as space does. We tend to experience time as something fixed and universal, a steady current moving at the same rate for everyone everywhere, 1 second per second, ticking forward without variation. This intuition is understandable. It matches our direct experience with reasonable accuracy. But it is wrong. Time is not fixed. It is not universal. It does not flow at the same rate in all places. This is not a metaphor or a thought experiment. It is a measured, confirmed, experimentally verified fact about the physical universe we live in. And nowhere in the observable cosmos is this fact more dramatically illustrated than at the boundary of a black hole, where time does not merely slow down but approaches a kind of absolute stillness that the human mind is not equipped to fully absorb. The phenomenon is called gravitational time dilation, and it falls directly out of Einstein's general theory of relativity. The basic principle is this: the deeper you are in a gravitational field, the slower time passes for you relative to someone in a weaker gravitational field. This is not a perceptual illusion. It is not that time seems slower, it is that time actually is slower, in the sense that physical processes genuinely unfold more slowly. Atomic clocks genuinely tick fewer times, and the aging of any biological organism genuinely proceeds at a reduced rate. The effect is real enough to matter in practical engineering. The GPS satellites orbiting Earth experience a slightly weaker gravitational field than we do on the surface, and as a result their onboard clocks run slightly faster than clocks at ground level. The difference is small, only about 45 microseconds per day, but it accumulates. If engineers did not correct for it, GPS systems would drift by roughly 10 kilometers per day. Gravitational time dilation is not a curiosity. It is a fact of the universe that engineers have to account for in the systems we use to navigate our daily lives. Now take that effect and scale it to the gravitational field of a black hole. Near the event horizon of a stellar mass black hole, the gravitational field is so intense that time dilation becomes extreme. An observer hovering just above the event horizon, somehow managing to resist the gravitational pull, would experience time passing at a rate enormously slower than a distant observer watching from far away. If you watched that person from a safe distance, you would see them moving in what appeared to be extreme slow motion. Their heartbeat would be stretched across hours of your time. Their words, if they were somehow audible, would be shifted to such a low frequency that they would fall below any threshold of human perception. And from their perspective, looking outward at the universe, they would see everything around them in extreme fast forward. The stars wheeling across the sky, light arriving blue-shifted and concentrated, the entire history of the universe appearing to unfold at a compressed, accelerated rate. The further they descended toward the horizon, the more extreme this asymmetry would become. At the event horizon itself, time dilation becomes, in the mathematical description, infinite. A clock at the event horizon, as seen from the outside, stops. It never reaches the boundary. It freezes there, infinitely approaching, infinitely slowed, never quite arriving. That is not a failure of the mathematics. That is the mathematics telling us something genuinely true about the structure of space-time at that location. For supermassive black holes, the ones at the centers of galaxies that Webb is observing, the situation has additional layers of complexity. The event horizon of Sagittarius A star, with its 4 million solar masses, has a radius of about 12 million kilometers. The tidal forces at that horizon, the difference in gravitational pull between your head and your feet if you were falling in, are actually quite modest by stellar black hole standards, because the horizon is so large that the gradient of the gravitational field across a human-sized object is small. But the time dilation is still extreme. Material in the innermost stable orbit around Sagittarius A star, the region of the accretion disk closest to the event horizon, is experiencing time at a rate measurably different from material further out. The infrared flares that Webb observes, those brief pulses of emission from the innermost accretion zone, carry spectral signatures that encode this time dilation in the form of gravitational redshift. The photons climbing out of that deep gravitational well lose energy in the process, their wavelengths stretching toward the red end of the spectrum. Webb's spectrographs measure that shift, and from it, researchers can calculate exactly how deep in the gravitational field the emitting material was located. But here is the element of the story that most people do not fully appreciate, because it moves from the strange into the territory that I can only describe as genuinely terrifying in its implications. If you were somehow transported to the vicinity of a supermassive black hole, and spent what felt to you like a single year in the intense gravitational field near the event horizon before returning to Earth, you might come back to find that thousands of years had passed here. Everyone you knew would be gone. Civilizations might have risen and fallen. The night sky would look subtly different as the stars moved in their orbits. You would be, in every meaningful sense, a traveller from the past, displaced by time not through any science fiction mechanism, but through the ordinary operation of general relativity in an extreme gravitational field. This is not a speculation about future technology. It is a direct consequence of the same physics that makes your GPS work. The only thing preventing it from being a practical concern is that no one is anywhere near a black hole, but the physics is real, the time dilation is real, and what Webb is showing us is the evidence of that dilation written into the light itself, in the stretched wavelengths of photons that had to climb out of one of the deepest gravitational wells in the universe to reach a golden mirror floating quietly in the dark. There is a detail about time near black holes that Webb's observations have illuminated in a new way, something related to the behavior of material right at the innermost edge of the accretion disk. At the innermost stable circular orbit, material that has been spiraling slowly inward through the disk reaches a point where stable orbits no longer exist. Inside this radius, there are no circular orbits that persist. Any material that crosses this boundary is on an unavoidable inward spiral toward the event horizon. It goes from being in the disk, following a roughly circular path, to falling essentially freely inward in what physicists call the plunge region. This transition is rapid. The material accelerates dramatically, and as it does, the time dilation it experiences increases sharply. Webb's reverberation mapping data has allowed researchers to probe the emission from this plunge region for the first time with sufficient sensitivity to distinguish it from the outer disk emission. The spectral signatures are distinct. The time dilation signatures embedded in the photon energies are measurably different. We are, in effect, watching time slow down in real time, encoded in light that travelled millions of light years to reach us. Lie here with that thought for a moment, in the quiet of wherever you are. Every photon of infrared light that Webb has collected from the vicinity of a black hole has made a journey that began in a place where time flows differently from the room you're resting in. It left an environment where a second is not a second in the way a second is for you, where the fabric of time itself is distorted by a mass so enormous that space curves closed around it. And it travelled across millions or billions of light years of expanding space, its wavelength stretched further by that expansion, until it arrived at a mirror made of gold, designed by human beings on a small rocky planet orbiting an unremarkable star, and was focused and measured and sent home as data. The universe allowed us to read the signature of distorted time in the light from its most extreme locations, and we built something beautiful enough to receive that message. In the history of science, there is a particular category of discovery that sits apart from all the others. Not the discovery that confirms what was predicted, which produces satisfaction and a sense of completion, the feeling of a puzzle piece clicking into place, and not the discovery that reveals something entirely new in a domain where nothing was expected at all, which produces wonder and excitement. The category I am talking about is the discovery that something you were certain you understood is wrong. Not slightly wrong, not wrong at the margins, in the way that a well-established theory sometimes needs minor corrections as measurement precision improves. Fundamentally wrong, in a way that means the entire framework you built on top of that understanding needs to be re-examined from its foundation. This is the rarest and most unsettling category of scientific discovery, and it is exactly what Webb delivered when it turned its infrared eye toward the early universe and began finding galaxies that had no right to be there. The standard model of cosmological structure formation, built up over decades through a combination of theoretical physics, computer simulations, and observational data from Hubble and other telescopes, makes specific predictions about what the early universe should look like. In this model, the universe began with the Big Bang approximately 13.8 billion years ago, and for the first few 100 million years, matter was distributed relatively smoothly, with only tiny fluctuations in density seeded by quantum processes in the earliest instance. Gravity then slowly amplified these fluctuations. Slightly denser regions attracted more matter. Over hundreds of millions of years, gas clouds collapsed to form the first stars, which were likely enormous, perhaps hundreds of times the mass of our Sun, burning bright and hot and dying quickly. These first stellar generations seeded the universe with heavier elements. Small galaxies formed, merged with each other, grew gradually larger. The first supermassive black holes assembled over hundreds of millions to billions of years by accumulating mass through accretion and mergers. The universe was young, messy, and still in the process of assembling its large-scale structure. This is what the models predicted. This is what researchers expected Webb to confirm. Instead, within the first year of Webb's science operations, researchers began finding objects that the model said could not yet exist. Galaxies in the data at redshifts corresponding to look-back times of more than 13 billion years, meaning we are seeing them as they were just a few 100 million years after the Big Bang, appeared not small and irregular and embryonic, but massive, structured, and in some cases already containing stars that appeared to be billions of years old. The stellar populations in these galaxies showed spectral signatures of mature stars, stars that had already lived through multiple generations of stellar evolution, stars that implied a star formation history stretching back further than the age of the universe, at the time we are observing them would allow. And at the centres of several of these impossibly early, impossibly massive galaxies were active galactic nuclei, supermassive black holes already containing hundreds of millions to billions of solar masses, actively consuming material and blazing with the energy of 1 trillion suns, less than 1 billion years after the universe began. The community response was cautious and methodical, as it should be. When an observation contradicts a well-established model, the first obligation of good science is skepticism toward the observation, not toward the model. Teams went through the Webb data on these early massive galaxies with painstaking care, checking the photometric redshift estimates that placed them so far back in time, looking for contamination from nearby lower redshift sources that might be masquerading as distant ones, testing the stellar population models used to interpret the spectral energy distributions, running the same analysis pipelines with different assumptions to see how sensitive the conclusions were to the choices made. The early results held up. Follow-up spectroscopic observations, which measure redshifts directly rather than inferring them from photometry, confirmed several of the most extreme cases. The galaxies were where Webb said they were as massive as they appeared, and they were not supposed to be there. The implications for black hole formation models are particularly severe. In the standard picture, the supermassive black holes at the centres of galaxies grew gradually, starting from stellar mass seeds, the remnants of massive first-generation stars, and accumulating mass over billions of years through a combination of accretion and mergers. Even under the most optimistic assumptions about how fast a black hole can accrete, there are physical limits. A black hole cannot consume material faster than a rate set by the balance between gravitational infall and the outward radiation pressure of the infalling material itself, a limit known as the Eddington rate. If you start with a stellar mass seed of perhaps 100 solar masses at a redshift corresponding to a few 100 million years after the Big Bang, and you allow it to accrete at the maximum Eddington rate continuously without interruption, you run out of time before you can build a black hole of several billion solar masses by the epoch at which Webb is finding them. The math simply does not work. Something must be different about how the first black holes formed, or how fast they grew, or both. Several theoretical responses to this problem have been proposed, and the scientific community is actively debating them. One possibility is that the first black holes did not form from stellar remnants at all, but from the direct collapse of massive clouds of primordial gas, bypassing the stellar stage entirely and forming black holes with initial masses of perhaps 100,000 solar masses, giving them a much larger head start on the growth trajectory. Another possibility is that early black holes went through periods of super Eddington accretion, consuming material faster than the standard limit, perhaps facilitated by the unique conditions of the early universe when gas was more abundant and less enriched with the heavy elements that create radiation pressure. A third possibility, the most unsettling one, is that the standard cosmological model itself needs modification at early times, that our understanding of how structure formed in the early universe is missing something fundamental. None of these explanations is fully worked out. None has yet been confirmed observationally. The data from Webb has defined the problem with extraordinary precision. It has not yet provided the solution. What Webb has done, and this is important to sit with, is force a reckoning. The models were not bad science. They were the best science available, built on solid physical principles and constrained by decades of careful observation. But the universe, it turns out, assembled itself faster and more efficiently than those models allowed. The first black holes grew faster than we thought possible. The first galaxies became structured and massive sooner than our simulations predicted. And the relationship between those early black holes and their host galaxies, the way they influenced each other's growth in the universe's first billion years, is more complex and more intimate than any picture we had drawn. Every one of those early massive galaxies Webb found, sitting in the data like a quiet anomaly that refuses to be explained away, is a message from the universe about something we got wrong. And the terrifying and wonderful thing about science is that those messages, the ones that break your model, are the most valuable ones it can send. There is a story we used to tell about black holes that went something like this. A black hole is a destroyer. It is the endpoint of stellar evolution, the grave of massive stars, a point of no return where matter goes in and nothing comes out. In this story, black holes are passive consumers, silent voids sitting at the centres of galaxies, growing slowly by swallowing whatever drifts too close, contributing nothing to the universe except their gravity. This story is not entirely wrong. Black holes do consume matter, they do grow, they are certainly among the most destructive environments in the universe in the immediate sense. But Webb's observations, combined with a body of evidence that has been building for 2 decades and is now being confirmed and extended with unprecedented clarity, have made it unmistakably clear that this story is catastrophically incomplete. Black holes are not just destroyers. They are, in a very real and measurable sense, among the primary architects of the universe as we see it today. The mechanism through which black holes build rather than simply destroy is one of the most energetically extreme processes in nature. When a supermassive black hole is actively consuming material, the accretion disk surrounding it does not just radiate light passively. It generates powerful magnetic fields, threading through the infalling plasma and twisting along the rotation axis of the black hole. These magnetic fields, interacting with the spinning space-time near the event horizon through a process described by a framework called the Blandford-Znajek mechanism, can extract enormous amounts of rotational energy from the black hole itself and channel it outward in the form of relativistic jets. Twin beams of plasma and radiation launched from the poles of the accretion disk at velocities approaching the speed of light. These jets are not small. They are not local phenomena confined to the immediate vicinity of the black hole. They extend for hundreds of thousands and in some cases millions of light years into the surrounding galaxy and beyond, carrying energy that dwarfs the combined output of every star in the Milky Way. What those jets do when they encounter the gas filling the galaxy around them is the crux of the story. A galaxy is not just stars, it is stars embedded in an enormous reservoir of gas and dust, the raw material from which future stars will form. This gas is called the interstellar medium, and its behaviour, whether it remains diffuse and hot, or cools and condenses into the dense clouds where star formation occurs, determines the entire future evolutionary trajectory of the galaxy. A galaxy with abundant cool dense gas forms stars prolifically, and grows rapidly. A galaxy whose gas has been heated, stirred and dispersed cannot form stars efficiently and gradually settles into the quiet, passive state we see in many large elliptical galaxies today. And what heats, stirs and disperses that gas? In a very large fraction of cases, the answer is the central supermassive black hole. Its jets punch through the galactic gas, depositing enormous amounts of energy, creating turbulence, driving outflows of material that can carry gas entirely out of the galaxy. The black hole, by consuming some material, prevents far more material from ever becoming stars. It regulates its own galaxy's growth. It acts as a thermostat for the entire system. This process, which astronomers call AGN feedback, where AGN stands for active galactic nucleus, has been theorized for 2 decades and incorporated into cosmological simulations as a necessary ingredient to reproduce the galaxy population we observe. Without AGN feedback in the models, simulations produce too many massive galaxies, too many stars, too much structure at the high mass end of the galaxy distribution. The simulations match the observations only when black hole feedback is included, which is a remarkable thing to consider. The universe we see, with its particular distribution of galaxy sizes and star formation rates, apparently required black holes to be as disruptive as they are. A universe without active black hole feedback would look meaningfully different. The architecture of the cosmos at the larger scales is in part a black hole artifact. Webb has added extraordinary new detail to this picture by allowing us to observe AGN feedback in action at epochs that were previously inaccessible. In the early universe, at the redshifts corresponding to the first 1 to 3 billion years of cosmic history, the rate of both star formation and black hole activity was far higher than it is today. This epoch, sometimes called cosmic noon, was when the universe was at its most productive, forming stars across billions of galaxies at rates that have never been matched since. It was also when the most powerful quasars blazed, when supermassive black holes were consuming material at extraordinary rates and launching the most energetic jets and outflows in cosmic history. Webb's spectroscopic observations of galaxies at these redshifts have revealed the signatures of those outflows directly. Superheated gas moving outward at thousands of kilometers per second, driven by the radiation pressure and jet energy of the central active nucleus, sweeping through the surrounding galaxy like a wind that empties entire regions of star-forming potential. But the relationship is not purely destructive in the broader sense. There is a complementary process, equally important but easier to miss, in which black hole activity does not suppress star formation but actively triggers it. The jets and outflows driven by an active galactic nucleus, as they push through the surrounding gas, can compress regions of that gas into densities high enough to initiate gravitational collapse and star formation, processes that would not have occurred without the disturbance. This is sometimes called jet-induced star formation, and Webb has now detected its signatures in several systems, finding bright clumps of newly formed stars aligned along the axis of powerful radio jets in galaxies where the black hole activity is clearly driving the compression. The black hole is, in these systems, acting as a midwife as well as a force of disruption, simultaneously suppressing star formation in some regions and triggering it in others, shaping the spatial distribution of stellar populations across the entire galaxy. What emerges from all of this Webb data, accumulated across hundreds of observations of black hole environments, ranging from our own galactic center to quasars at the edge of the observable universe, is a picture of a cosmos far more interconnected and mutually regulated than the simple story of stars and gravity that most people carry in their heads. Every large galaxy in the universe has a supermassive black hole at its center. The mass of that black hole correlates tightly with properties of the surrounding galaxy, its total stellar mass, the velocity dispersion of its stars, even the density of its dark matter halo, correlations so tight that they cannot be coincidental. The black hole and the galaxy grew together, influenced each other, regulated each other over billions of years. They are not separate objects that happen to coexist. They are a coupled system. And the universe we live in, with its particular arrangement of galaxies and star formation rates and chemical abundances, is the product of that coupling played out across 13.8 billion years. The black hole at the center of our galaxy is not a foreign object sitting in the middle of our cosmic home. It is, in a profound sense, one of the reasons our cosmic home exists at all. We have spent a great deal of time tonight discussing what Webb can see, the flares and echoes and spectral signatures, the impossible early galaxies, the jets and outflows reshaping entire cosmic structures. All of it extraordinary. All of it real and measurable and encoded in data that human beings built instruments sensitive enough to receive. But now I want to talk about something Webb cannot see. Something no instrument will ever see, because the laws of physics themselves forbid it. I want to talk about what is at the center of a black hole, not the event horizon, not the accretion disk, not the surrounding environment, but the thing at the very middle, the singularity. Because understanding what we do not and cannot know about this point is, in many ways, more important than everything we have learned. It is the place where our entire understanding of physical reality breaks down completely, and what that breakdown means has implications that extend far beyond astrophysics into the deepest foundations of how we think the universe works. The singularity, as it appears in general relativity, is a point of infinite density and infinite space-time curvature. These infinities are not a description of something real, at least not in any way we can currently interpret. When a physical theory produces an infinity as an output, it is almost always telling you that the theory has reached the edge of its domain of validity, that you are applying an equation to a situation it was not designed to handle. General relativity is our best description of gravity and space-time on large scales and at high energies. It has been tested to extraordinary precision in every accessible environment. But it does not include quantum mechanics. It does not describe the behavior of matter and energy at the smaller scales, where the uncertainty principle and quantum fluctuations dominate. And at the singularity, all the mass of the collapsed star is compressed to arbitrarily small scales, far smaller than any scale where quantum effects can be ignored. General relativity reaches the singularity and produces infinities because it is the wrong tool for that environment. It is like trying to measure the temperature of a star with a household thermometer. The instrument is not wrong in general, it is just not built for that. What is needed, and what physicists have been searching for throughout the second half of the 20th century and into the 21st is a theory of quantum gravity, a framework that successfully unifies the principles of general relativity with those of quantum mechanics, and can describe what actually happens at extreme densities where both sets of rules apply simultaneously. Several candidates exist. String theory proposes that the fundamental constituents of reality are not point particles, but tiny vibrating one-dimensional strings, and that the different vibrational modes of these strings give rise to the different particles and forces we observe. Loop quantum gravity proposes that space-time itself is not continuous, but is woven from discrete quantum units of area and volume, a kind of pixelation of space at the smallest possible scale. Other frameworks exist as well, each with their own mathematical architecture and their own set of predictions. None of them has been confirmed experimentally. None of them has produced a clear, unambiguous prediction that has been tested and found correct, in a way that distinguishes it from the others. The theory of quantum gravity remains the most important unsolved problem in fundamental physics. What this means for the singularity is that we genuinely do not know what is there. This is not a gap that is likely to be filled soon. We cannot send a probe. We cannot observe it even indirectly, because the event horizon prevents any information from the singularity from reaching the outside universe. We can theorize, we can build mathematical models and work out their implications, but we cannot in any currently conceivable way test those theories against observation. Some physicists believe that a correct theory of quantum gravity will show that the singularity is not actually a point of infinite density, but rather that quantum effects halt the collapse at an extremely small but finite scale, the so-called Planck scale, where the density is unimaginably high but not infinite. In some speculative models, this quantum bounce produces a new expanding region of space-time, a new universe, on the other side of what was the singularity, a universe that, from our perspective, is completely inaccessible, but that, in a profound sense, was born from the collapse of matter in ours. There is another problem at the boundary of the black hole, less famous than the singularity but in some ways more troubling, because it implicates not just gravity, but the entire framework of quantum mechanics as well. It is called the black hole information paradox, and it was first clearly articulated by Stephen Hawking in the 1970s. Hawking showed, through a remarkable calculation combining quantum mechanics and general relativity, that black holes are not truly black. Due to quantum effects near the event horizon, pairs of virtual particles are constantly being created just outside the boundary. Occasionally, one particle of the pair falls inward, while the other escapes outward as real radiation. This process, now called Hawking radiation, causes the black hole to very slowly lose mass and energy over an enormous timescale. A black hole with the mass of our Sun would take approximately 2 × 10 to the power of 67 years to evaporate completely through Hawking radiation, a timescale so vast it makes the current age of the universe look like an eye blink. But the principle is established. Black holes do not last forever. The problem is this: every piece of matter that falls into a black hole carries information, in the precise physical sense of the word, the specific quantum state of every particle that composed it, every detail of its structure, temperature, composition, and history. Quantum mechanics contains an iron rule called unitarity, which says that information cannot be destroyed. It can be scrambled, redistributed, made practically inaccessible, but the total information content of a closed system is conserved. Yet if Hawking radiation is truly random, carrying no information about what fell in, then when the black hole finally evaporates completely, all that information is gone, destroyed, and that would be a fundamental violation of quantum mechanics. The two most successful theories in the history of physics are making contradictory demands at the black hole. One says information cannot be destroyed, the other seemingly says it is. This paradox has occupied some of the finest minds in theoretical physics for 50 years. A leading current proposal, inspired partly by string theory, suggests that information is somehow encoded in subtle correlations in the Hawking radiation, scrambled to an extreme degree but not truly lost. The details of this encoding remain unclear. Webb's observations of black hole environments cannot directly resolve the information paradox, but they probe the physical conditions at the edge of the event horizon with greater precision than ever before, and every new constraint on the physics of that boundary is another piece of the puzzle placed on the table. The singularity and the information paradox are the two places where the universe is most clearly telling us that our map is incomplete. They are not failures of science, they are its most urgent invitations. There is a question I want to place in front of you now, quietly, without urgency. I want you to hold it the way you might hold a stone you found on a walk, turning it over in your hand, feeling its weight, not trying to solve it, but simply letting it exist in your awareness. The question is this: what if the Big Bang was not a beginning from nothing, but an emergence from somewhere? What if the event we call the origin of our universe, that initial instant of unimaginable density and temperature from which space and time and matter and energy all expanded outward, was not the first thing that ever happened, but was instead the consequence of something that happened before it, in a place and in conditions we have no direct access to? And what if the thing that caused it, the mechanism that gave rise to the universe you're lying in right now, was a black hole? This idea, which sits at the boundary between theoretical physics, cosmology, and the kind of speculation that scientists are cautious about putting in peer-reviewed papers, but will discuss quietly at conference dinners, goes by several names. Lee Smolin, a theoretical physicist at the Perimeter Institute in Canada, developed one version he called cosmological natural selection. In Smolin's framework, every black hole that forms in our universe creates a new region of space-time through a quantum bounce at the singularity, a new expanding universe on the other side. This new universe would have physical constants, the specific values of things like the speed of light, the strength of gravity, the mass of the electron, that are slightly different from those of the parent universe, analogous to genetic mutation in biological reproduction. Universes that produce many black holes have many offspring. Over cosmic generations, the population of universes would be dominated by those with physical constants that maximize black hole production. And here is the thing most people do not immediately notice about this idea. A universe optimized for black hole production is also, it turns out, a universe optimized for the existence of long-lived stars, heavy elements, complex chemistry, and the conditions that allow life to emerge. The same physical constants that make our universe hospitable to us are the ones that make it extraordinarily productive of black holes. A separate but related framework comes from the mathematics of general relativity itself. When you look carefully at the equations describing the interior of a black hole after the collapse has proceeded past the event horizon, you find a region of space-time that, in its structure, shares deep mathematical similarities with a Big Bang cosmology. The infalling matter, past the event horizon, is in a region where the spatial dimensions contract and time becomes the only direction of evolution. Some theorists have pointed out that this is structurally analogous to the initial singularity of an expanding universe. Viewed in reverse, the collapse that creates a black hole in one spacetime might, in this picture, be the flip side of an expansion that creates a new spacetime. Our Big Bang and the black holes in our universe might be manifestations of the same fundamental process, viewed from opposite sides of the same mathematical boundary. Now, to be precise about what we know and what we do not, these ideas are speculative. They are not established science in the way that general relativity or quantum mechanics are established science. They have not produced clear, tested, confirmed predictions that distinguish them from alternatives. Some versions of the black hole cosmogenesis idea make predictions that are, in principle, testable, but the tests require a level of precision in measuring fundamental physical constants and their potential variability that lies beyond current technology. Smolin's cosmological natural selection framework makes a specific prediction that the fundamental constants of our universe should be near optimal for black hole production. Whether this is actually true is a matter of ongoing investigation and debate. Some analyses suggest it is approximately correct. Others find significant room for improvement. The framework is alive but unconfirmed. What Webb's observations add to this conversation is indirect but significant. The discovery of massive black holes in the early universe, already containing billions of solar masses within the first billion years after the Big Bang, means that black hole formation began earlier and proceeded faster than standard models predicted. If black holes give rise to new universes, then our universe was an extraordinarily productive parent from very early in its history, seeding new spacetimes at a rate that the previous generation of cosmological models would have underestimated. Webb's data also contributes to our understanding of the large-scale structure of the observable universe, the distribution of galaxies and voids and filaments that formed from the initial quantum fluctuations of the Big Bang. Some theorists have noted that the statistical properties of this structure, the specific patterns in the cosmic microwave background, the detailed shape of the power spectrum of density fluctuations, might carry faint imprints of pre-Big Bang physics if the universe did indeed emerge from a previous spacetime. The analysis of Webb's deep field data is being used to probe these statistical signatures with greater precision than was previously possible. But let me bring this back to something more immediate, something you can sit with in the dark right now without needing equations or theoretical frameworks. If our universe exists inside a black hole, then the event horizon of that black hole is the absolute boundary of everything. Not the boundary of what we can observe, which is already unimaginably large, but the boundary of what exists for us in any meaningful physical sense. Beyond it, in whatever parent universe gave birth to ours, there is a region of space-time that is as inaccessible to us as the interior of a black hole is inaccessible to the matter outside it. We cannot send signals there. We cannot receive signals from there. We cannot even, strictly speaking, ask what it looks like, because the question assumes a shared reference frame that does not exist across an event horizon. We are in this picture not merely small in a large universe, we are enclosed, contained, nested inside a structure that itself exists inside a larger reality we can never access. And there is one more layer to this that I find genuinely difficult to hold in mind, without feeling something that I can only describe as a quiet vertigo. If black holes in our universe give rise to new universes, and if those universes also form black holes that give rise to further universes, then the structure of reality is not a single cosmos, but an unimaginably vast, possibly infinite branching tree of space-times, each one born from a collapse in a parent universe, each one producing its own generations of black holes and offspring cosmoses. We would be one node in this structure, unable to perceive any other node, separated from our cosmic ancestors and descendants by boundaries more absolute than any distance. The universe you live in, with its particular stars and galaxies and black holes and empty spaces, would be both a descendant of something that came before and the parent of things that will follow. Every black hole Webb observes, every collapsing core and infalling accretion disk and spiraling flare at the edge of a near event horizon, might be a birth as much as a death. The most violent events in the cosmos might be, from a perspective we can barely formulate, the universe's way of continuing itself into realities we will never see. Let me bring us home for a moment. We have travelled a long way tonight across time and distance, from the engineering history of a golden telescope to the edges of the observable universe, from the mathematics of singularities to the speculative possibility that our entire cosmos was born from a collapse in a parent space-time. These are large journeys. They are the kind of thinking that can make you feel very small and very far from anything familiar. So let us come back now to something closer. Not the abstract supermassive black holes of distant quasars, blazing with the energy of trillions of suns in galaxies we will never visit. Not the theoretical constructs of quantum gravity or cosmological natural selection. Let us come back to the specific black hole that has been part of your life since the moment you were born, the one around which every person who has ever lived on this planet has been quietly, continuously orbiting. The one sitting 26,000 light-years from the bed you are lying in right now, Sagittarius A star, our black hole. Our Sun orbits the centre of the Milky Way at a speed of approximately 828,000 kilometers per hour. That is an extraordinary speed by any human measure, faster than any spacecraft we have ever built, fast enough to circle the Earth in under 3 minutes, and yet it takes our solar system approximately 230 million years to complete a single orbit of the galactic centre. We are in a galaxy so vast that even at nearly 1 million kilometers per hour, the journey around it takes longer than the dinosaurs existed before the extinction event that ended their era. In the approximately 4.6 billion year history of our solar system, we have completed about 20 orbits of the galactic centre. 20 years in the life of the Milky Way, 20 loops around Sagittarius A star. The solar system is, in this frame of reference, quite young, and through every one of those orbits, through every geological era and mass extinction and evolutionary transition that has occurred on this planet, Sagittarius A star has been there, sitting at the centre, anchoring the rotation of the galaxy. Not actively feeding most of the time, not blazing as a quasar, not launching continent-shattering jets of plasma, just existing in its current quiet state, maintaining the gravitational structure that holds the 400 billion stars of the Milky Way in their orbits. The galaxy's shape, the spiral arms, the central bulge, the distribution of stellar populations from old red stars near the core to younger blue stars in the spiral arms, all of it exists in the context of the gravitational environment that Sagittarius A*'s mass helps define. Remove it, and the galaxy would not simply continue as before. The central dynamics would change. The orbits of stars near the core would shift. Over long timescales, the structure of the entire inner galaxy would evolve differently. It is not merely a resident of the Milky Way. It is one of the foundational gravitational pillars upon which the Milky Way's architecture rests. But Sagittarius A* is not completely silent. Webb's observations of the galactic center have confirmed and extended what ground-based infrared telescopes first detected years ago: the black hole flares. Several times each day, the region around Jesker A* brightens briefly in infrared and X-ray wavelengths, each flare lasting anywhere from a few minutes to a couple of hours before fading back to the quiescent baseline. These flares are not dangerous to us at this distance. 26,000 light-years is an enormous buffer, but they are a reminder that the engine is not off, it is idling. Small amounts of gas and dust occasionally drift close enough to the innermost accretion zone to be disrupted and heated, producing these brief pulses of radiation before being consumed. In 2013, astronomers observed a gas cloud called G2 approach Sagittarius A* and be tidally disrupted and partially consumed, producing an uptick in flaring activity that Webb's predecessors monitored closely. The black hole noticed, it responded. It is aware, in the purely physical sense, of everything that enters its gravitational domain. Here is something I want you to feel, rather than just understand. The gravitational influence of Sagittarius A* does not stop at some neat boundary, 26,000 light-years from the center. Gravity has no cut-off distance. It weakens with the square of distance, becoming vanishingly small, but never exactly zero. The gravitational pull of Sgr A* on our solar system is extraordinarily weak compared to the Sun's pull on the planets, so weak that it has no measurable effect on the orbits of Earth or any planet in our system on any timescale relevant to human civilization. But it is not zero. The 4 million solar mass black hole at the center of our galaxy is, right now, exerting a gravitational pull on every atom in your body, on the atoms of the bed beneath you, the walls around you, the air in your lungs. The pull is immeasurably small, but it is real. You're in gravitational relationship with Sagittarius A*. You have been, every moment of your life, without knowing it, without feeling it, without any way of sensing it directly. And yet the relationship is as physically real as the gravity holding you to the Earth. Webb has given us something extraordinary in its observations of Sgr A*, a window into the present activity of our own galaxy's central engine, with greater sensitivity and spectral richness than was previously achievable. The flare data, the reverberation mapping of the innermost accretion zone, the monitoring of stellar orbits in the dense cluster around the black hole, all of it accumulating into an increasingly detailed portrait of the object that has been at the center of our cosmic home for longer than the Earth has existed. Some of those orbiting stars have periods of years to decades, orbiting the black hole at distances comparable to the scale of our solar system, but at speeds that would carry them from the Earth to the Moon in seconds. Watching them move year by year in the data from ground-based and space-based telescopes is one of the most viscerally direct demonstrations of a black hole's existence available to science. You watch stars arc across the sky at speeds that only an invisible object of 4 million solar masses could produce. The black hole writes its signature in the motions of the stars around it, and we have learned to read that signature. There is something quietly profound about the fact that the closest supermassive black hole to Earth is in our own galaxy, bound to us by the same gravitational structure that binds every star in the Milky Way into a single coherent system. We are not observers of Sagittarius A* in the way we are observers of distant quasars, separated from them by cosmological distances and look-back times of billions of years. We are participants in the same gravitational system. Sgr A* is family, in the most extended cosmic sense of that word. It shaped the environment in which our galaxy formed, regulated the star formation history that eventually produced the Sun, contributed to the chemical enrichment of the interstellar medium from which the solar system coalesced. The iron in your blood was forged in stellar cores and scattered by supernovae in the Milky Way over billions of years, in a galaxy whose shape and star formation history was partly regulated by a 4 million solar mass black hole sitting quietly at its centre. You are, in a chain of physical causation that is long but unbroken, partly a product of Sagittarius A star, and tonight, for perhaps the first time, you know its name. There is a particular kind of honesty that science demands of itself, one that is easy to admire in the abstract and genuinely difficult to practice in the specific. It is the honesty of saying clearly, without apology and without false modesty, exactly where the knowledge ends and the ignorance begins. Not the performed humility of someone who knows the answer but pretends uncertainty for social reasons. Not the strategic vagueness of someone who wants to seem more open-minded than they are. But the real thing, a precise, careful accounting of what the data shows, what it does not show, and what it cannot show given the instruments available and the laws of physics as we understand them. Webb has shown us extraordinary things. Tonight we have travelled through many of them. But Webb has limits, and those limits are not embarrassments to be minimised or footnotes to be quickly passed over. They are in many ways the most interesting part of the story, because the edge of what we can know is exactly where the next generation of questions lives. The most absolute limit is the one imposed not by engineering, but by physics itself. The event horizon of a black hole is, by definition, a one-way boundary for information. Nothing that crosses it outward can ever reach Webb's detectors, because nothing that crosses it outward can exist in our universe in any form that carries a signal. Webb can map the accretion disk. It can measure the reverberation echoes from material just outside the horizon. It can track the spectral signatures of gravitational redshift in photons climbing out of the deep gravitational well. But it cannot see past the horizon. The singularity, whatever is actually happening there, whatever the correct theory of quantum gravity describes as the true physical state of matter at that extreme density, is permanently, irreversibly, and completely hidden. This is not a temporary limitation waiting to be overcome by a better telescope or a more sensitive detector. It is a structural feature of the universe. The event horizon is not an obstacle between us and the answer. It is the universe's statement that some answers are not available from the outside, by any means, ever. Within the domain of what is in principle observable, Webb still faces significant practical limitations in its black hole science. The resolution of Webb's images, extraordinary as it is not sufficient to resolve the accretion disk structure of even the nearest supermassive black holes as a spatially extended object. When Webb observes Sagittarius A star, it is seeing a point source of infrared emission, not a resolved disk with identifiable structure at different radii. The reverberation mapping technique extracts spatial information from temporal data, from the timing of echoes, rather than from direct imaging. This is powerful but indirect. A future space-based infrared interferometer, combining the signals from multiple widely separated telescopes in space, could in principle achieve the angular resolution needed to directly image the accretion disk of SGR-A star at infrared wavelengths. No such instrument currently exists or has been funded. Webb is the best infrared eye we have, and it cannot quite see that detail. The disk is there, the physics is happening, but the image remains below the resolution threshold, a blur within a blur, inferred rather than shown. For the distant early universe black holes, the ones at the heart of Webb's most disruptive discoveries, the limitation is different but equally fundamental. Webb can detect these objects because they are extraordinarily luminous, pouring out energy at rates that make them visible across billions of light years. But detecting them is not the same as characterizing them fully. The spectroscopic data Webb can obtain from a quasar at a redshift of 7 or 8, meaning we are seeing it as it was when the universe was less than 1 billion years old, is limited by the faintness of the source, even for Webb's unprecedented sensitivity. Exposure times of tens of hours are required to obtain spectra of sufficient quality to measure physical parameters like black hole mass, accretion rate, and outflow velocity with meaningful precision. And even with those long exposures, many of the spectral features that would most directly probe the physical conditions in the accretion disk are either redshifted out of Webb's wavelength range or blended with other features in ways that require complex modelling to disentangle. The data is rich. It is also incomplete in ways that matter for the deepest questions. There is also the question of what Webb cannot see, because it does not look in the right part of the spectrum. Webb is an infrared telescope. The physical processes around black holes produce radiation across an enormous range of wavelengths, from radio waves to X-rays to gamma rays, and the full picture of what is happening in a black hole environment requires all of those wavelength windows simultaneously. The infrared emission Webb captures traces specific physical processes: the thermal emission from dust, the spectral lines of certain ions, the near-infrared flares from the innermost accretion zone, but the X-ray emission traced by Chandra probes different temperature regimes. The radio emission mapped by the Event Horizon Telescope traces magnetic field structure. The gamma-ray emission detected by the Fermi Space Telescope traces the most energetic processes in the jets. No single telescope, however powerful, captures the full picture. The complete physics of a black hole environment lives across the entire electromagnetic spectrum simultaneously, and understanding it fully requires coordinating observations from multiple facilities in multiple wavelength regimes. Webb is a crucial piece of that puzzle. It is not the whole puzzle. And then there is the deepest limit of all, the one that sits not at the level of instrumentation, or wavelength coverage or angular resolution, but at the level of theory. Webb produces data. Data requires interpretation, and interpretation requires theoretical models that tell you what physical processes should produce what observational signatures. When Webb finds a galaxy at redshift 10 that is more massive than the models predicted, the significance of that finding depends entirely on how confident we are in the models. If the models are well constrained, the discrepancy is a genuine crisis. If the models have more freedom than we realized, the discrepancy might be accommodated without fundamental revision. Sorting out which situation applies requires not just more observations but deeper theoretical work, simulations with higher resolution and more complete physics, and the patient, unglamorous work of propagating uncertainties through every step of the analysis chain. Science at the frontier is not a series of clean revelations. It is a slow negotiation between data and theory, each one constraining and reshaping the other over years and decades. All of this, every limit and gap and unresolved question, is not a reason for disappointment. It is a reason for something closer to reverence. The fact that Webb, the most powerful infrared telescope ever built, the culmination of 30 years of human engineering and scientific ambition, still faces these limits tells you something important about the nature of what it is studying. Black holes are not objects that yield their secrets easily. They are places where the universe keeps its deepest rules, where the frameworks we use to describe reality reach their edges, where the next layer of understanding is waiting behind a boundary that we are not yet equipped to cross. Every unanswered question Webb has generated, every discrepancy it has revealed between observation and prediction, every edge where the data runs out and the theorists take over, is an invitation. The universe is enormous and strange and far from fully understood, and that is, when you let yourself feel it fully, one of the most beautiful things about being alive at a moment when we are finally beginning to look. We have come a long way tonight. We started in the quiet of a control room, with technicians and cold coffee and numbers scrolling across screens, in the moment before a golden telescope turned toward the darkest places in the universe. And we have travelled together through the physics of collapsing stars and the geometry of event horizons, through the engineering of a sunshield colder than Pluto, and a mirror made of gold thinner than a thought, through the flares of Sagittarius A star and the impossible galaxies of the early universe, through time dilation and gravitational echoes and the information paradox and the speculative possibility that we ourselves are living inside a black hole in a parent cosmos we can never access. It has been a long journey. And I want to take a few minutes now, before we part for the night, to sit with what it means. Not the science, which we have covered as carefully as we can, but the meaning. The human weight of what we have been talking about. Think about what James Webb actually is. Not in the technical sense, not the mirror segments and the sunshield and the L2 orbit, but in the larger sense. It is a decision made by human beings to spend 30 years and $10 billion and uncountable hours of collective intelligence on the single act of seeing more clearly. Not seeing more clearly in order to make something. Not seeing more clearly in order to solve a practical problem or generate economic value or defend a border. Seeing more clearly for its own sake, because there are things out there that we do not understand, and the not understanding feels to some people like something that needs to be addressed. This impulse, The impulse to look further and more carefully at the universe simply because it is there and because it is mysterious is one of the oldest and most distinctly human things we do. It predates writing. It predates agriculture. Long before there were telescopes, there were people lying on their backs in the dark looking up at the stars and feeling the pull of the question, what is that? How far does it go? What happens at the edge? Webb is the latest and most powerful expression of that impulse, and what it has found, in its observations of black holes and the early universe and the impossible galaxies that should not exist, is that the universe is stranger and more complex and more interconnected than our best models had captured. The early black holes grew faster than they should have. The first galaxies assembled more quickly than the simulations predicted. The light near an event horizon bends in ways that push the edges of what general relativity describes. Time slows near the horizon in ways that are real and measurable, and at the centre of every large galaxy in the observable universe, including ours, there sits a supermassive black hole that has been shaping the history of its galaxy for billions of years, regulating star formation, launching jets that dwarf entire stellar populations, and sitting at the gravitational centre of a structure that contains hundreds of billions of stars, each one a sun, each one possibly orbited by worlds, all of them turning quietly around an invisible point of infinite density that our mathematics reaches and cannot pass. Here is the thing I want you to really feel, in this quiet moment before sleep. The atoms in your body were forged in the cores of stars that lived and died before our sun existed. The carbon in your cells, the oxygen in your lungs, the iron in your blood, all of it was cooked in stellar interiors and scattered by supernovae across the Milky Way over billions of years. You are, in the most literal physical sense, made of ancient starlight, and the stars that made you existed in a galaxy whose structure and star formation history was shaped, in part, by a 4 million solar mass black hole at its centre. You're downstream of Sagittarius A star in the most direct causal sense. The conditions that allowed your solar system to form, the chemical enrichment of the interstellar medium, the regulation of star formation rates across the history of the Milky Way, all of it connects back, through a long chain of physical cause and effect, to the black hole that has been sitting at the centre of your galaxy since before the Earth existed. You are, in a very real sense, a product of a black hole, and tonight, through the intermediary of a golden telescope floating in the dark, you looked back at it. We are the universe noticing itself. This is not a poetic exaggeration. It is a precise description of what is happening when a human being lies in the dark and thinks about the physics of event horizons and the behaviour of light near a singularity. The universe is 13.8 billion years old. For most of that time there was no awareness in it, no capacity for wonder, no ability to form a question and pursue an answer. Matter organised itself into stars and planets, and, on at least one small rocky world orbiting an unremarkable star in the outer region of a spiral galaxy, into living things that eventually developed nervous systems complex enough to model the universe they found themselves inside, to ask questions about origins and endings, to feel the pull of the unknown as something that demands a response. We are the mechanism by which the universe has begun, very recently in cosmic terms, to examine itself. Every observation Webb makes, every photon it collects from the vicinity of a black hole, is the universe gathering information about its own deepest structures through the instrument of human curiosity and human engineering. The darkness that Webb looks into is not empty. It never was. It is full of the most extreme physics in existence, full of bent space-time and slowed time and light echoing around impossible curves, full of the seeds of galaxies and the engines that regulate their growth, full of questions that our best theories cannot yet answer, and boundaries that our best instruments cannot yet cross. And somewhere in that darkness there are answers waiting. Not all of them, probably not most of them. The universe is under no obligation to be fully comprehensible to the nervous systems that evolved on one of its smaller planets, but some of them. Enough to keep asking, enough to keep building, enough to send another golden mirror further into the dark and wait for what it sends back. Thank you for staying with me through all of this tonight. It means something, genuinely, that you chose to spend these hours in the company of black holes and golden telescopes and the oldest light in the universe. If this journey through the cosmos gave you something to carry into your dreams tonight, please take a second to like this exploration or subscribe to join us on the next one. It is a small gesture, but it helps this channel reach more minds that carry the same curiosity you do. And now, let the questions settle. Let the scale of it wash over you without trying to hold it all at once. Tonight you learned something about the darkest places in the universe, and about the strange, improbable fact that you're here to ask about them at all. The next time you step outside on a clear night and look up at the band of the Milky Way stretched across the sky, remember that somewhere in that soft glow, hidden behind 26,000 light-years of stars and dust, something with the mass of 4 million suns is sitting quietly at the centre of everything, and that a golden mirror 1 million miles from Earth has looked toward it and brought back light from its edge. Sleep well tonight. You're made of stars, you're orbiting a black hole, and the universe, through you, is slowly learning to understand itself. Good night.